For Section 2.2, we're kind of getting into briefly into atomic structure. So each element is composed of certain atoms. So hydrogen atoms of hydrogen, they're all very similar. Atoms of helium are all very similar. Atoms of carbon are very similar to each other. We consider the atom, it's like the smallest kind of piece of matter that kind of retains or has all the properties of it, like that element. So an atom of carbon has all of carbon's properties. If you were to take that atom and make it smaller, somehow, that atom of carbon, that is, it's not going to be carbon anymore. It's going to be something else. Okay, so it's the smallest unit of an element. Our atoms have component parts to them. They're protons, neutrons, and electrons. When you think of protons, think positive. Protons are positive, electrons are negative, and then neutrons are neutral. They don't have an electric charge. Protons and electrons could possibly attract each other. Protons and protons could potentially repel each other. Same with electrons can potentially repel each other. Neutrons are neutral. They don't care. So think, with electrostatic charges, opposites attract, and similar electrical charges repel each other. Protons and neutrons, they're found in the middle of an atom, and electrons are on the outside in an area we call the electron cloud. Protons and neutrons have mass. We just kind of round it to 1. It's like 10 to the negative, negative 29th kilograms or something like that. It's really, really tiny. So we have something called atomic mass units. Sometimes they're called Daltons, or sometimes they're measured in Daltons. So neutrons and protons have a mass of 1. Electrons, their mass is about 1/200th of a proton. So for the most part, it's just 0. Electrons are on the outside of the middle, which is called the nucleus. And here you have a couple representations of what an atom could look like. And you might not have any red flags, so I'll raise some red flags for you. So first of all, it would be really hard to draw these to scale. So, you have a nucleus, and you can see there's positive charges in the middle. Those are protons. And then there's something without any charges. It's just kind of drawn in like a sphere. Those are the neutrons. So this has two protons and 2 neutrons in the nucleus in the middle. On the outside, you can see on the right-hand side here, we have 2 negative charges, and these are the electrons. On the left diagram, which is the same atom, it's kind of fuzzy, so it's kind of the electron cloud. It's just hazy. Here, because the electrons, we like to know exactly where they're at any given time, but we really can't know. Here, the electrons are kind of drawn in an orbit, like they're going around the sun or something. It doesn't necessarily work that way, but for us, this is good enough for government work. So some of the red flags I'm going to raise here is that these electrons and protons, if we're just drawn to scale, they're too close together. So if we had a nucleus that size, say we were at Oakton at the Ray Hartstein campus, and we're standing in the front door, we would expect, if we had a nucleus that size, our electrons would probably be by Lincoln Avenue and Cicero or Skokie Boulevard. So there's a huge gap. It ends up that atoms are mainly empty space. Okay, but you couldn't draw a book like that where you're kind of like folding out like the page till you get to 500 meters away or whatever. It just doesn't work that way. So hopefully get the idea and just realize it's not drawn to scale, and atoms are actually mostly empty space. So then another thing is, on the previous slide, I just got done telling you that like positive charges repel each other, and but yeah, then I show you this slide here of two protons that are right next to each other, and then along with two neutrons, and there's a force that we don't really talk about. Well, I'm going to, but we don't really talk about in biology, and because I don't really understand it. It's called strong force. That's what's keeping this nucleus together. We actually expect it to spontaneously break apart, but I think we have enough neutrons actually to prevent that. And also, these are pretty close together, the protons and the electrons. You'd almost expect the protons to pull the electrons into the nucleus or something like that, but that doesn't happen because they are so far apart, or that's potentially one of the reasons. Anyway, so there's kind of our model of an atom, and it's some things to think about is like the mass is all located in the nucleus. Nucleus is positive, and outside of the nucleus it's negative. So we have opposite electrical charges, and that's going to come into play later on. I'm not going to really go over this too much, but each element differs from each other based on its atomic number, and the atomic number is really just the number of protons that element or atom has. So for instance, hydrogen has one proton. If I add another proton to it, it's no longer hydrogen, it becomes something called helium. But you can change the mass of an atom. You can add neutrons, say even to hydrogen. You can add neutrons to hydrogen. As long as you're not changing the proton number, it's still going to be hydrogen. You're just making it either more or less massive, depending if you're adding or subtracting neutrons. So some of you might be asking, well, how do I do that? Well, you probably don't really do that yourself, but in nature it can happen. And then if you have two atoms of the same element, we call that an isotope. And why is this important? Well, because we can, isotopes can be used for various things. And we have radioactive isotopes, which are probably the most interesting ones, that you'll just have an atom and it'll spontaneously break apart, giving off particles and then energy potentially. And then this can be used in medicine. It can also be used in science to determine the date of something really old. But in medicine, it's interesting because people can ingest radioactive isotopes, whether it's like iodine or something else, and then it can be used as imaging to figure out where that iodine is going to, or where some other barium or whatever is going to, and you can figure out metabolism and among some other things. And here's a person. This is I think it's a cat or a PET scan, and presumably there's some radioactive iodine in there, and they found some cancerous throat tissue. So anyway, can be used like the half-lives. So we kind of have an idea if we have certain isotopes. The half-lives of them, and then it can be used for determining the date of something really old. And we actually can use radioactive like uranium to estimate the age of the universe. In life sciences, they're using more things like carbon 14 versus carbon 12. Anyway, and then I'm going to stop here. So it's not really within the scope of our class, but it is in the textbook, just kind of discussing electrons and their energy levels. So we're not really going to get into kind of bonding and how that works. We will probably talk about energy levels and electrons when we go over photosynthesis, but at this point, I'm not going to go into a very large discussion. So that is 2.2 for us.